Hello again. Welcome to the second lecture. At the end of the first lecture, we talked about the van der Corput sequence, and then we learned about how we can different van der Corput sequences together to obtain higher dimensional sequences, and those are called Halton sequences. And here's an example. This is a van der Corput sequence in base 2, and this is the van der Corput sequence in base 3, and now we're going to couple them. The first terms, 1/2, 1/3, and that's going to be our first vector, two-dimensional. And then here are the second terms, third terms, and so forth, and that is our the first 4 elements of our two-dimensional Halton sequence. And here is a plot of, if I'm not mistaken, I have 500 vectors here. And this picture is a nice picture. This picture tells a lot about low discrepancy sequences and what they try to do. Low discrepancy sequences try to partition the space, approximate the space, fill the space. And space, by space, I mean the unit cube here, as evenly as possible, as uniformly as possible. Now, pseudorandom vectors, when you plot them, they show you, they give you a picture that looks a little more different. Discrepancy sequences. Pseudorandom vectors give us a much more haphazard way of filling the unit cube. You see some gaps every now and then. You see some clusters. And so, this is randomness. It's not the evenness of the partition that's emphasized. It's the randomness, the unpredictability. So, differences in a visual way. I'm going to give you another picture. This is going to be the first 1,000 vectors of the Halton sequence. Now I'm going to increase the basis to 7 to 29. And then you get this very interesting picture. All the first 1,000 vectors lie on this region, a small strip, and a little of them are at the top. Now, so if we were using this sequence in simulation, say numerical integration, we would be getting bad approximations if you use these first 1,000 vectors. The entire space is really just empty. The sequence, the first 1,000 vectors of the sequence has only sampled, like the diagonal. Now, does this mean sequence in these bases is not 2D mod 1 of the cube? No, it doesn't mean that in the limit, as n goes to infinity, it is going to start eventually filling all parts of the unit cube, but it's not doing it in a very efficient way. This phenomenon is usually called high correlation between higher bases, because the basis numbers are large, and this was first observed by Burton, Weller, and Four in late 70s. And as a remedy, as a solution, researchers introduced permuted corpus sequences. This is at the top, the original definition of the van der Corput sequence. And look what we're going to do. We're going to insert a permutation, apply a permutation sigma b to each digit. A permutation, what is a permutation? What is sigma b? Well, it's just a function, a bijection on the digit set. So it will just take these digits and send them elsewhere, just permute them. And a further generalization looks at, considers different permutations at each digit. And then you can take these permuted van der Corput sequences and then you can couple them to obtain permuted Halton sequences in the usual way. Several permutations have been introduced in the literature, and some of these permutations are obtained by using some heuristics, and some of them are obtained by searching for some optimal permutations that minimize the discrepancy of the one or two-dimensional projections of the sequence. Okay. Now I want to have a different type of an object. I'm going to talk about TS sequences, TMS nets. These two are related to each other, nets and sequences. One of them is the finite version of the other. And as an example of a TS sequence, I'm going to talk about the 4 sequence. Okay, so we'll start with this definition. This is a definition of an elementary interval in base B. Okay, so given this base B, given S the dimension, and an elementary interval is a subinterval of the S-dimensional unit cube that has the following form. So we're looking at a product of some intervals. It's going to be much easier to understand this definition if you look at some examples. So let's just look at some simple examples. I'm going to take my base to be 3, and I'm going to take S to be 1. So we're just talking about, one-dimensional intervals. And and if you take D1 to be 0, well, D1 is the exponent that you see here. When J equals 1, this is D1. If that number is 0, you just get 1 as the denominator, right? And then AJ can be then 0, and then 1. So that's how you end up with just 0, 1. If D1 equals 1, okay, so if this number is 1, that means now we are dividing in the interval into 1/3, and the AJs are, the constants that you can get, the coefficients that you can get as you go along. It's like 0 to 1/3, then 1/3 to 2/3, and 2/3 to 1. If you take the exponent D1 to be 2, then you're dividing the interval into 9ths, and then these become your elementary intervals. So it's just your interval divided into 9ths. Now let's look at a two-dimensional case. S equals 2, and the base is 2 as well. So let's look at something more interesting. So let's look at this last one. D1 equals 1, D2 equals 2. 1 means you are dividing the x-axis into 0, 1/2, and 1/2, 1 only. D2 equals 2 means you're dividing the y-axis into 4ths, 1/4, 1/4, 3/4, 4/4, and then you take the Cartesian products all of these intervals, okay? And those are your elementary intervals. Okay, so now, what is a TMS net? So this definition is a definition of a TMS net. But instead of trying to explain this definition, let me go over this example. In this example, I'm taking T to be 0 in the definition, M to be 3, and S to be 2. And there's also B, base, it's 2. So now I'm going to describe to you what a 0, 3, 2 net in base 2 is. First of all, this is a finitely many vectors. Okay, how many? Well, it is b to the power m points. M is 3, b is 2, so we are talking about 2 to the power 3 points, 8 points, 8 vectors in dimension 2. Okay. So then, going back to the definition that says every elementary interval in base B of volume B to the power T minus M. What is B to the power T minus M in my example? In our example, T was 0. So we end up with just B to the power negative M. B is 2, M is 3, so that gives us 1/8. So every elementary interval of area 1/8 contains exactly 1 point. Let's look at an example. These points that you see there are, let's count them, how many? 3, 5, 8. You see 8 points in the two-dimensional space, and these points actually form a 0, 3, 2 net in base 2. And the reason is, you look at all elementary intervals of area 1/8, and these are all of those. These horizontal rectangles, you can check that each one of them has area 1/8, and there are a total of eight of them. You can look at the intervals. They go from 0 to 1/8, 1/8 to 1/4, 1/4 to 1/2, just like how we defined elementary intervals. And similarly, this one partitions the space into vertical rectangles of area 1/8. And in this case, it's 1/2 width, height is 1/4. So anyway, all these pictures, these 4 pictures, give us all possible division of this unit cube into elementary intervals of area 1/8 and base 2. And if you look at, in each case, you will see that every subinterval contains only 1 point of the sequence of the net. So that's what it means to be a 0, 3, 2 net. And notice that this definition allows us to find evenness or uniformity. We define the space into subdomains of equal areas, and then we require that the sequence has 1 point in each subspace, and that's an attempt. I mean, what it means to say that a sequence is evenly filling the unit cube. And a TS sequence is an infinite version of a TMS net. So an infinite sequence, Q1, Q2, etc., is called a TS sequence in base B if I take the first b to the power m elements, that is a TMS net in base B, and then the next b to the power m and the next b to the power m. So all of those b to the power m parts of the sequence will give me finite TMS nets. And the 4 sequence is an example of a TS sequence where T equals 0. In addition, you see the word digital here. Digital refers to a special construction of TS sequences. I'll explain that construction in a minute. And the base of the 4 sequence, by the way, is the smallest prime number greater than or equal to S, where S is the dimension. So here is how one constructs a digital TS sequence, or the framework of the construction for digital TS sequences. So bold Q is my S-dimensional digital TS sequence in base B. And here I want to switch to vector notation. So this is the name of the sequence, and this vector is the nth term of the sequence. And it's a vector of S components, as you see. The components are in the superscripts, and as n goes 1 to infinity. So I want to tell you how Q is obtained. I want to tell you how this vector is obtained. And in particular, I should explain how the ith component vector, Qn superscript I, is computed. So let me write this number in its base B expansion. Okay? And this base B expansion, I'm looking at just finite expansions. If it's not finite, I'm truncating after k digits. So I want to know, or I need to tell you, how these C's are obtained. What is C1? What is C2? Then we're coming close. Now let's take little n and write little n in its base B expansion. Little n is an integer, and here's its base B expansion. Okay, so this is given. We know what this is, but we know what these digits are. We want to know what these digits are. And we're going to obtain these C's, the CI's from the AI's using this operation. The C's, I'll put them in a vector. are obtained from A's by this matrix vector multiplication. So here I introduce now the matrix that this is a new matrix that I didn't tell you about before. And these matrices, so that it has a superscript I, so that means for each dimension, you have a corresponding matrix. And these matrices are called the generator matrices of the sequence. And different digital sequences have different generator matrices. And for the case of the 4 sequence, the generator matrix, kth generator matrix, is p to the power k minus 1, where p is the Pascal matrix mod p. I don't want to go into the details. The definition of the Pascal matrix is here, and there's a remark that allows us to compute these matrices quickly, but I think I can skip those details. Now let's talk about use low discrepancy sequences in numerical integration. So this is my numerical integration problem. I want to integrate a function f over the s-dimensional unit space. So I as 0, 1 to the power s. And let's assume the value of the integral is theta. In both Monte Carlo and quasi-Monte Carlo, we estimate this integral by computing the average of our function when it's evaluated at some vectors, some numbers xn. In Monte Carlo, these xn's are coming from a pseudorandom sequence, and in that case, theta n, the estimate of the integral, converges to theta as n goes to infinity almost surely. This is known as the strong law of large numbers. And then the error, theta n minus theta, is a normal random variable with 0 mean and this variance. Okay, so once again, these results follow from probability theory. In quasi-Monte Carlo, the xn's are now coming from an s-dimensional UD mod 1 sequence. There's nothing probabilistic about this. And then theta n converges to theta as n goes to infinity, and that's one of the theorems that we talked about before. Now what we are interested in is what can we say about this error, theta n minus theta. And here comes the classical inequality. We are looking at the absolute value of the error that we were just talking about. The inequality tells us that this error is bounded by the product of terms. This first term is the variation of the function in the of Hardy-Krauss. Second term of the discrepancy of your sequence, the first capital N elements of your sequence. Now, the function f has to have a finite bounded variation for this inequality to be true. Now, early on, we mentioned that the best low discrepancy sequences satisfy a star discrepancy of log n to the power s over n. And so that tells us that if we integrate functions in this way, using quasi-Monte Carlo sequences, the error will have that order of convergence. Variation of the function will be just a constant. And if you can come up with sequences with smaller discrepancies, then you'll be making the upper bound for the error smaller. I want to quickly talk about the variation in the sense of Hardy-Krauss, and really quickly. Variation in one dimension, if you have a one-dimensional function, to find its variation, the interval 0, 1, you would partition interval 0 to 1. Then you would look at how much your function increases or decreases as you go from one end of the interval to the next. In S dimensions, we do something similar. We partition each axis, and there are now S axes. And then we define these difference operators, delta J, which essentially fixes everything but the jth component. And then it looks at the function difference, the difference in the function values for that component as in the partition you go from Vi to Vi plus 1. And so it's really a straightforward generalization of dimension 1, but the notation is a little complicated. And then this operator is just a composition. So delta J1 through JP means you take the operator delta JP and take its composition with the next one and so forth. In dimension 2, this definition becomes a summation of your function values on the corners of the square, and then the signs the function takes go like this: plus minus plus minus. Then the variation of f of tally is the supremum, the summation of all these differences. And then the variation of f in the sense of Hardy and Krauss looks at the projections of the function and the variation of the projections in the sense of Vitali, and then looks at the summation. Fairly complicated to work with as a concept. Now, the drawbacks of the Koksma-Hlawka inequality. On F, the inequality can be loose. What I mean by that is, given function f, this left-hand side, the actual error could be much smaller upper bound. And if that's the case, the upper bound is not going to be, not going to give you an idea how big the error is. If what you're trying to do is assess the error is, it's not going to be useful. Even if it was useful, if you wanted to compute this upper bound, that would be very difficult. Okay, computing the variation, our discrepancy, are difficult. Discrepancy is an NP-hard problem. And another difficulty of variation in the sense of Hardy and Krauss is that it's too restrictive in the following sense. It's a two-dimensional function. It only takes values 1 and 0. I mean, the function is obviously finite. It only takes the values 1 and 0. Define the function on a unit square. This function has infinite bounded variation in the sense of Hardy and Krauss. The inequality does not apply. We cannot numerically approximate the integral using low-discrepancy sequences. Well, that we can. We just did the numerics. We would see that we get very good approximation to the integral. Now, there is a different error bound, a different approach to the QMC error, and that avoids this concept of functions of bounded variation. And I want to talk about that briefly. This is called uniform point sets, and you can think of that as a generalization of TMS nets. So we start with a general probability space. If you think, picture in your mind a space X. Draw some space X, a Venn diagram in your mind. And you put a measure on it, mu, and then you have measurable spaces. And on this space, you have a script M, which is a collection of subsets of X. And then you have script P, which is a point set of elements of this space X. So these are like our vectors. And then I have the counting function. The counting function A counts how many elements P belong to M. Then we say script P, the point set, is M mere uniform if for all M in script M this equality holds. This equality. The numerator is just the number of points in script P that fall in the set M. And then you divide that by capital M, that's the number of vectors, that's the number of elements in your point set. That average, that relative frequency, is exactly equal to the measure of that space. This notion is the same notion that we talked about earlier when we talked about TMS nets. Once again, basically, you take a space, you partition the space into some equal measure subspaces, and then if your point set puts equal number of allocates equal number of elements, you need subspace. Equal in the sense that the relative frequencies are going to be equal to the actual measure of the subset, and we say we have a uniform point set. Now, these uniform point sets were introduced by Niederreiter, who also proved a number of error bounds. And here is one, and in this case, script M consists of subsets, give us a partition X. I probably used the word partition before, but script M in general doesn't have to be a partition. And what is a partition? A partition is just subsets that are disjoint, and their union is your space X. Let's have a look at this inequality. On the left-hand side, you just see the integration error, right? Your abstract integral over the space X using the probability measure mu. And here's your estimate. This integral is bounded by the summation of k terms. Term is the measure of each set in your partition here, and it's multiplied by the supremum of the function on that set mj minus the infimum of the function over that set mj. So all we need to have is that the function to be bounded. If this is finite, the sup is finite. If the infimum is finite, then we have an error bound that will give us a finite upper bound. So unlike Koksma-Hlawka inequality, this error bound does not require bounded variation, finite bounded variation, but only requires boundedness. So in the last part of the second lecture, I will talk about randomized quasi-Monte Carlo methods. I mentioned that the Koksma-Hlawka inequality had some drawbacks. We want to be able to, when we do a quasi-Monte Carlo integration, when we simulate or integrate a function using a quasi-Monte Carlo sequence, we want to be able to assess how accurate the approximation is. So we want to have an idea on the error. And Koksma-Hlawka inequality doesn't really help with that. It doesn't give us a practical way of measuring error. In Monte Carlo, on the other hand, one can use statistical methods, descriptive statistics, to analyze the error. You can compute estimates, and then their variance, their standard deviation, in a very practical, very easy way. So randomized quasi-Monte Carlo allows us to analyze error in the context of low discrepancy sequences, just like Monte Carlo. So let's start with beta. Let's beta. What is it? What's beta? Beta is a low discrepancy sequence, and then we will be able to obtain random copies of beta. Okay, so I will tell you how to do that in a little bit. But for now, imagine that there is a way to take beta and then just randomize it. You know, turn this into a different sequence at multiple times. These are going to be all statistically independent. And if I am trying to compute this integral, and I am going to use beta I, obtain an estimate theta I by simply the standard way. We'll compute the function average on the elements of beta I, and that's going to give you theta I. And once you do that for all the betas, you are going to end up with estimates theta 1 through theta m. If these estimates, if these theta I are statistically, independent, and then you can take their mean, their sample mean theta hat, and then you can estimate the error by computing the sample variance of the theta i's. Here in this formula, I have theta, but of course theta is not known, so you estimate that by so let's just to summarize, in randomized quasi-Monte Carlo, we start with beta, and we are able to randomize that. So I'm going to write this as beta subscript u. U is some random parameter. So every time you get a sample from you, you obtain a new sequence. And then I'm going to define this function. This is really a random variable, theta of beta u, as the average of my function on the elements of beta u, the first capital N terms. And then in a practical implementation, I will be sampling from this random variable u and obtain u1 through um. And for each one of them, I have an estimate for the integral, and then I am taking the average of all of those. I will talk about a couple randomized quasi-Monte Carlo methods. And most methods, randomized quasi-Monte Carlo methods, satisfy these two properties. If you take the expected value of Q of beta u, Q is this randomized quadrature rule that we talked about. This is a random variable because u is a random variable. So the expectation is going to be the same theta, the integral that we were trying to estimate in the first place. And the variance of theta, not the variance of the quadrature rule, satisfies this error bound. And if you look at this term, you see that this is the square of the error term of this for the star discrepancy of a low discrepancy sequence. And in some of the RQMC methods, with additional assumptions, this can be reduced further. And here is a list of some randomized quasi-Monte Carlo methods that I'm going to talk about now. The random shifting is easy to explain, it's easy to apply. So as an example, let me look at the first 6 Halton vectors in dimension 2 using bases 2 and 3. Now let's say I want to randomize this using random shifting. To do that, you are going to generate some random numbers, and of course these are pseudo-random numbers, u1, u2, let's say. And let's say these numbers turn out to be 0.74 and 0.62. And then you are going to shift all of these vectors, your Halton vectors, by this vector u. Okay? Shifting means you will be doing a component-wise addition, vector addition. So this is, you know, 1/2 was the first Halton vector. So you add your 0.74 and 0.62 to that. And then the braces means if the number is greater than 1, just take the fractional part. Okay, so this is like, for example, 1.24. You're not supposed to go beyond 1, right? So you take the fractional part, 0.24. Shift using the same vector u to all the other Halton vectors. That gives you a new set of vectors. If we take the 0, 3, 2 net that we talked about earlier, and if we shift it by this random vector u, this is the picture. This is the picture that we are going to obtain. Okay. Next, scrambled nets of nets and sequences, and I will describe scrambling method, which is due to Owen, introduced in mid-90s, and I will explain this method by applying it to 032 net we talked about earlier. And here is, by the way, our 032 nets. And also in this table, you see the x-coordinate and the y-coordinate of each pair, and its base. Read this. The first step is to scramble the first coordinates. Okay, random permutation of the digits, 0, 1. Say we pick a permutation that sends 0 to 1, 1 to 0. Apply it to the first digit of coordinates of each vector in the net. So, for example, the x-coordinate of this vector, 1/64, right? That's 0. So you will have to flip that, and that's going to be 1. And then the next vector, the first digit of its x-coordinate is 1. So then you have to flip 1 to 0, and that's how we obtain this 0. So you continue like that. Finish all the first digits of the x-coordinates. And geometrically, the effect of this scrambling is to swap the 2 half rectangles. 0, 1/2. So this is the first, look at the first half rectangle in this picture. And then this is the second half. The second half of the rectangle. I hope you can see that red marker, and you can see what I mean by the first half and the second half. And then if you swap those two, okay, if you just change their locations, this is the picture that you're going to get. Now these 3 aligned black dots appear over here because they're switched. So that's what scrambling the first digits does. Now we move on to the second digits, which is going to be a little more complicated. In this case, we need 2 random permutations. Okay, generate 2 random permutations at random. Let's say the first permutation is the one that flips the digits, and the second permutation is the identity permutation. Use the first permutation to scramble the numbers whose first digits are 0. What do I mean by that? The x-coordinates in the first table, and identify those numbers where the first digits are 0. One's given in red. We're going to apply that first permutation that flips the digits to the second digits of only these numbers. For example, this one, where we have a 0, it's right here now, and the second digit here was 0, so when you apply the permutation, you flip it at 1. And then the next number is going to be this number, okay? You're going to apply the permutation to this one, the second digit, it becomes 0. And as you can guess, you use the second permutation, the other permutation, numbers whose digits are 1. well, before we talk about that one, geometrically, the effect of this permutation is to swap the rectangles 0, 1/4, 1 and 1/2 the y-axis. So what we are doing now is look at the first half, and then you look at the two halves of the first quarter and the second quarter, and then you swap those two. Then you do the second permutation, as I mentioned a minute ago, and then you continue like this until you finish all the digits and all the dimensions. And eventually what you obtain is a scrambled version of the 032 net. And Owen proved this theorem for scrambled sequences. Many researchers in subsequent work proved these variance results for smooth functions. The Mathématiques introduced a number of scrambling methods that approximates Owen's scrambling method. They are faster to implement, they're easier to implement, and these methods limit the amount of randomness in the original scrambling method in return for efficiency. And I want to describe two of those, digit scrambling and linear scrambling. Random digit scrambling, you generate one independent random permutation for each digit of the x and y coordinates. So what does that mean? Going back to our 032 net, if you look at this table, you see that each the x coordinate has how many digits? 6 digits. And the y coordinates have 6 digits too. So 12 digits in total. And we're going to generate 12 random permutations. Okay. And let's say the random permutations we obtain are phi and d, and in this list, ID means simply the identity permutation, and phi is the one that flips. Let's take phi and apply phi to all the first digits of the x coordinates, and we'll take ID and apply it to this to the second digits of all the x coordinates. And you see that now done right here on this page. Phi is now being applied to the first digits of the x coordinates, and then you get this new sequence. And you continue doing it for all the other digits. And this is the picture that you obtain when you digit scramble the 2 net that we talked about before. Linear scrambling, little scrambling, digit scrambling. Linear scrambling, we generate S lower triangular matrices denoted by L superscript. Non-diagonal entries, random integers between 0 and p-1. P is the base. I think I earlier might have used as the notation for base. Diagonal entries are random integers between 1 and p-1. So you cannot have 0 on the diagonal. Generate vectors, S vectors, G superscript K, between 0 and p-1. Early on, we talked about digital TS sequences and how to generate. And to generate a digital TS sequence, we multiplied the generator matrix by the vector whose components were the coefficients of the digit n. And that product actually gave us the coefficients of the real number q and k when it's written in its base b expansion. So this function phi is pointing to those coefficients. We are going to update this definition And we are going to replace the generator matrix CK by LK multiplied by the original CK. Right? And also we are going to add a shift, to the operation. So that shift G superscript K wasn't here in the original definition of a digital. So that's added there. Well, in practice, the results, this GK was just a zero vector. The scrambling randomization is done actually by this product. And once again, the generator matrix is based by a random matrix multiplied from the left. And this is a special kind of a random matrix as described. Now, the last topic, start-Halton sequences, and I'm going to go through this quickly. The way to think about the van der Corpus sequence way, to think about the van der Corpus sequence using ergodic theory. Now, the von Neumann Kokotana transformation, if I'm not mistaken, is the first example of an ergodic and measure-preserving transformation on the unit intervals 0, 1. So this is a mapping, a transformation from 0, 1 to 0, 1, and it's constructed in an inductive way. So here's how the construction goes. It's the construction uses the so-called splitting and stacking process. You take the unit interval and you divide it into two pieces, 0, 1/2, 1/2, 1, and you stack the second piece at the top of the first piece. And then you are going to split these intervals from the middle, okay, just along those dashed line. And then you are going to take this these two subintervals, 1/4 to 1/2, and then 3/4 to 1/2, 3/4 to 1. And then you're going to move them, stack them at the top of these subintervals. That's how you get 0, 1/2 here, and then the other intervals there. This is the splitting and stacking, and you keep doing it. And at each iteration, at each step, you're actually defining a mapping T from a subset of 0, 1 to 0, 1, and then in the limit, this becomes a full mapping from 0, 1 to 0, 1. Interesting, as far as we are concerned, is if you look at the orbit of 0 under this mapping, of 0 means 0, and then its image. The image of 0 is just under this mapping. The image of 0 is simply the number that is right, over 0. So this transformation T is a linear mapping. It linearly maps the interval at the bottom to the interval at the top. So 0 is mapped to 1/2. 1/2 is mapped to 1/4. 1/4 is mapped to 3/4. That is precisely the van der Corpus in H2. So that was the critical observation. And then you can generalize this to a multi-dimensions by taking a vector of back. And here I should mention that the splitting and stacking was done in this picture by dividing everything into pieces and then into 4 pieces, 8 pieces. Nothing special about it. Could have started with splitting the interval into 3 pieces, 3 equal pieces, and then take each subinterval and then divide it into 3 sub-pieces. So that would be like the base 3 for the van der Corpus sequence. Do this in general for any base B. And that allows you to generalize the von Neumann Kokotana transformation using a one-dimensional von Neumann-Kokotana transformation on each axis, using different B1 through BS. And then under this generalization, the orbit of zero vector under TB, the Halton sequence basis. And when you have an ergodic mapping, you have the luxury of using Birkhoff's ergodic theorem. Birkhoff's ergodic theorem says that if you look at the orbit of any vector x, and once again, the orbit means you apply the mapping to x repeatedly. You find t of x and then t of x and t of x, that's the orbit. The orbit is a UD mod 1C almost surely. And that means you can use the orbit to integrate a function using our standard quasi-Monte Carlo integration. I'll skip that last bullet. We can also incorporate permuted Halton sequences in this setting. But let's move on. Now, randomized Halton sequence, permuted Halton sequences by randomly selecting starting values U, and then by taking the orbit of U under the von Neumann-Kokotana transformation using base B, and then we evaluate our function on that orbit. We take the average, and that's going to be our randomized quadrature rule. Okay, and then it turns out that the expected value of this randomized quadrature rule is theta, as we expected, and its variance satisfies this bound if the following conjecture is true. I will probably not go through this conjecture now, but I will leave it to you if you're interested in reading more about it. And that is going to be the end of my lecture 2. In lecture 3, we're going to talk about how to generate random numbers from different distributions, how to simulate stochastic processes, and how we can use them in option pricing. Thank you and see you next time.